Okay, welcome to the class. I will start with a new topic, recursive definitions. So this is recursive definitions, and this is section 8.8. In the new topic is not on this test. It will be on the next one. The test does stuff up to last week, so up to strong induction. Okay. Let me start by showing some recursively defined objects that we already know, and kind of like review different types of recursions that we have already seen. So the first one, a factorial function. And for convenience, I will talk about objects which are defined inductively. There is some natural induction variable. So the base case will be for n equal 1, and then a recursive case will define all the values after 1. Okay, factorial function can be defined like this. So f at 1 is 1, and then for all inputs larger than this, the value of the function at argument n is defined recursively as n times the value of the function at one argument less. And if you enveloped this recursion and showed a closed form, then what would you get? So fn is n times the previous one. What is the previous one? Well, you run the recursive code again. F of n minus 1 is n minus 1 times f at n minus 2. So the next thing that you will be multiplying is n minus 1, and so on. If you now, and here is f of n minus 2. So if you ran the code again, you will have n minus 2, dot, 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 dot. Eventually, you will come down to the value at 0.1, which is defined by the base case. So this is a recursive definition of a factorial. Let's look something else, like powers of some base b. The base case, the function is defined as b, because b to the 0, b to the 1 is b itself. In a recursive case, the function at, and the function in this case, I'm calling it f in both cases, right? That is an arbitrary choice. F of n is b times f of n minus 1. And again, with recursion, if you now look, what is f of n? Well, it's b times f of n minus 1, which is b times f of n minus 2, which is b times f of n minus 3, and so forth. You loop, 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 until you again hit the base case. And how many you have? N. So this is b to the n, right? Very similar code defines a different function. Okay. Now we can also look at it as, now this was as a function. Well, we can also do it as a sequence, a recursively defined sequence. We call those recurrence relation. But they were nothing but recursive way of defining sequences. So the first element of the sequence, and I call it the sequence S, again, an arbitrary choice. The first element is B. Then, and after that, I define sequences recursively. Nth element is B times the previous element. So that's we call that a recurrence relation, but it's a recursive definition of a sequence. And of course, because it's a one-to-one, right? In fact, we define sequences as functions from integers, right? So there's a one-to-one relation between this definition and this definition. They are one and the same thing, right? Where basically you define Si as f of I. Okay, also compare to recursive algorithms. So for example, a factorial algorithm. What would be the recursive algorithm for a factorial? And here I'm assuming n greater or equal to 1. Well, the algorithm could be like this. If n is the base case, return 1, and else return, and here is the recursive call, return n times the algorithm recursively called on one smaller value, right? On the same input decremented. And this code is one-to-one with this recursive definition, right? In the base case, the function returns 1. That's exactly what's written here. If this is not met, so therefore you are in this case, the function returns n times the sort of the same function on decremented argument. That's exactly the definition here, right? So basically, each of these definitions is a recursive algorithm in disguise, right? In a rather thin disguise. Here's how we are going to generalize this stuff today to say, okay, we can also recursively define the definition. We can have a recursive definition of a set, and you know, for example, set I'm going to call S, but this is you know, S is arbitrary name, just like in this case, it's function f or sequence S, right? All of these were arbitrary names. So a recursive definition will consist, just like these recursive things, of two basic things: base case and a recursive case. We call them rules in this more general case of sets definitions. And really, sets is really the same thing as data structures. Because you'll see soon why that is. So basis rule, basically you have to specify some elements of S explicitly. So you're going to declare some elements as for sure members of the set. These will correspond to the smallest data structure examples. You know, like say you're defining a linked list, well, you will define an empty linked list, or perhaps a linked list with a single element. Okay, as definitely your linked list, the smallest kind of linked list. And the second is that we will have a recursive rule or many rules. Just like there can be several elements created in the set by the basis rule, there will be possibly several elements that are created by the recursive rules. And what these recursive rules have to do is specify new elements of S as some functions, some function or functions, in case there's many rules, of existing elements. Perhaps only if these meet some predicates. In other words, So these rules will look like this. If an element, let's say A, is in set S, then I will create new element of set S based on that A. Think of a linked list prepended by another node. So a linked list incremented by one more element. But perhaps it's only with some predicates, like, so I would do that only if this linked list had some property, like for example, it was non-empty. Okay, you will see sometimes these predicates are useful. And there is a third, these recursive rules will exactly be like there's recursive cases in these definitions, where if you think the definition of a sequence is already satisfies this. We have basically a set of values that we call Si. There is S1, S2, S3, S4. These values form a sequence. We say that this set contains a guy we call S1, and we equate him with B. And then we say, well, if the set contains something like Si, then it will also contain Si plus 1, which will be equal to B times Si. That will be the case of the recursive rule. The third thing is so-called exclusion statement that you can see once and then basically assimilate its meaning, and then basically for never mention it again, which is a statement that says S contains only elements created by rules, either the basis or the recursive. Okay, and that statement will be the same no matter what you define. So therefore, basically you don't need to repeat it. The point is that the basis rule will say the following things belong to the set. The recursive rule say if something belongs to the set, then so does something new. But they sort of don't exclude that perhaps yet something completely different can belong to the same set as well. Well, this is excluded by this exclusion statement. Let's see this in an example. Okay. So here is an example. So let's see example. Binary strings set B star of all binary strings. Now, you might recall that we had a non-recursive definition of set of all binary stars, binary strings. This is a set of bits. B to the n is B cross product with B n times. So this is a set of n bit strings, and B star is defined as a union from 1 to 0 to infinity of Bi. In other words, it's B0 and B1 and B2 and So these are 0-bit strings, 1-bit strings, 2-bit strings, and so forth, right? So B star contains all bit strings. B to the 0 is a set that contains only an empty string. Okay, so these were the non-recursive definitions of bit strings using Cartesian products and sum of, and a sum union notation. Okay, here is the recursive definition. The basis rule is that an empty string, we declare it to be a bit string. So here this is my set S, right? I'm calling him B star. I'm going to define B star using recursive method. I declare an empty string to be a member of B star. And also I have the following recursive rules. You know, maybe I should call these things. So this is the base rule. And now I'll have recursive rule number 1. And the rule will be, if X is in B star, then X0 is in B star. In other words, if X is a bit string, then X concatenated with a 0 is also a bit string. You have to be careful, and it takes some time to get used to this. What is a variable? What is a constant? And what does this mean that I'm placing 2 objects next to each other? This means concatenation of strings. And it's by context that you're going to figure out, you know, what these symbols correspond to. The second recursive rule is that although we'll try, if we think ahead, you know, as okay, you can possibly be confused, we'll disambiguate. We'll say this stands for string concatenation, or we'll try to do that. So, and that, the second rule is that if X is in the set, then so is X concatenated with bit 1. Okay, and that's it. So this is a quite concise recursive definition of a string of bits. Let's see how this definition works. Okay, so let me copy it over here in a concise form. So so recursive definition of B star looks like this. Base case, the empty string is a member of B star. The recursive rule 1 is that if X in B star, then X0 in B star. Recursive rule 2, if X in B star, then X1 in B star. Okay, so the way you should interpret such a recursive definition is B star, and then there is this invisible exclusion statement that nothing else is in B star but elements that are created either by the base rule or by some application of recursive rules. So let's see how these rules can function to create a set. We'll here have in this column count number of applications of the recursive rules, and here perhaps you know, if we do use recursive rule, then recursive rule variables, basically, what are we using? And here elements added to set B star. So the simplest case is no recursive rules. So therefore, the only element added to the B star is what is added by the base case. So this is not important. And we're adding one element to the base, in the base case, an empty string. Okay, let's try to use the recursive rule once. Okay, so let's try to use RR1. And RR1 says the following: if X is in the set, then so is X0. Well, how can X be instantiated? The only X for which this statement is true is X equal lambda. So we have no choice the only way to instantiate this rule and make this true is to set X to be this empty string. So, and what is added to this set if X is an empty string? Well, it's an X concatenated with 0. So it's an empty string concatenated with a 0. Well, that is just 0. Concatenation of an empty string. So this stands for empty string. And LX is, or sorry, LS is equal to S for any S, right? If you concatenate an empty string to something, you get that thing. So we're adding a 0 using this first recursive rule. What about the second recursive rule? Again, so far in the set is just this empty set. So we sort of make a bar here. And we are just looking at what are the new elements added to the existing set, which is just this singleton of this empty string. So if X is an empty string, we are adding in the second rule alpha 1, which resolves to 1. Okay. So we added a 0 and a 1 using a single run of these recursive rules. Let's do recursive. Let's look. How does the set look, set B star, if you do 2 applications of the recursive rule? Let's look at recursive rule number 1. And now we have more choices. X could be this, or that. Now, using X equal lambda is not productive. We could do it, but all that we would do is add again 0 to the set. And we know that the set, I can add the same element over and over to the set. It doesn't change anything. If an element is already in the set, it makes no difference to add it again. So we can just as well skip that part, right? So X alpha skip, because you've already done this. So the more productive thing is to take rule 1 with X equals 0. If we take it with X equals 0, this is a 0. So what do we add? X0. But X is 0. So we're adding 0, 0. And that is a new element in the set. What about there is one more possibility, take 1, right? If X is 1, then we're adding X0 resolves to 1, 0. So we're going to add this. And recursive rule 2, again, X equals lambda, we can skip. And instead, let's look what recursive rule 2 adds when X is 0. Well, it will add 0, 1, which is new. And with X1, it will add 1, 1, which is new. So basically, now perhaps you can see that I'm going to now add all 3-bit strings. And if I do 4, then I will add all 4-bit strings, etc. Right? So a tiny recursive code, and it generates all bit strings, right? By the recursive application of these recursive rules. Okay, let's look at another example. Okay. 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 Let's define recursively set properly nested parenthesis strings. It's a set of properly nested parenthesis strings, okay? It's okay, I will write that set of properly nested parentheses strings. What do I mean by properly nested? So let's consider an alphabet which contains two characters, open bracket and a closed bracket. So this is not a C and an inverse C. This is open bracket and this is closed bracket. Okay, so this is my alphabet. I can consider string A star, set A star, it's a set of all strings made of elements of A, right? So just like B star was a set of all bits, A star is going to stands for all strings made of these elements, right? Now, P and PS is going to be a subset of A star, which contains things like that, because it's open, closed. And it also contains open, open, close, close. Or it contains open, close, open, close. This is properly nested. Perhaps open, open, close, open, close, close. And I can go on, right? Like there's many possibilities here, but doesn't contain things like open, open. So this is not good. Or close, open, or close, close, and so on and so forth, right? So okay, here is how could we, in fact, it's not very clear how to define a set of properly nested parentheses strings without recursion, without using recursion. So let's see how possibly we can define it recursively. So here is a draft of a recursive definition of this P and PS set. The basis, well, how about this? That my atomic expression that is in the set is open, close. And I will declare it to be a properly nested parenthesis string. The recursive rule, I will have, well, how about this? Well, I will have two. First, if A is in P and PS, then if I open, then put whatever string A is after that, and then close. So this stands for concatenation of an element character open bracket from this set. Then whatever string this is, it will be a subset of this. So it will be, this string will be an element made of over this alphabet, and then close. That this new string is in P and PS as well. But so I could use this recursive rule to create this character, this string, because if I instantiate this rule with A, so who is in the set now? Well, it's this guy by base rule. That's it. If I use recursive rule once, okay, then I have no choice here. A has to be this string. And if it is that string, then what this recursive rule will add is open, and then my A, which was open, close, and then close again. That's exactly how this string is built. But can I use this one? Can I build this one? I cannot, right? Because the recursive application of this rule will just create strings like this, right? So if this is my new A, then I will add this. And so I will add with like more and more open, and then followed by the same number of close, but nothing else. Not this, not this. I need a second rule. So perhaps the rule could be this. If A, B are both parentheses P and PS strings, then so is their concatenation. Now, this rule looks good because it actually is capable of generating this string. If A is bound to this element that sits in the set by the base rule, and B is also bound to this, because nothing says that A and B have to be different. A and B are both elements of P and PS. A is equal to this, and also B is equal to this. Then so is their concatenation. Well, you will exactly generate this string using that, right? That's it. That's my definition. And let's do the similar exercise of looking at the number of recursive rule applications. Look at which rule, what variable, how am I binding the variables, and new elements added. Okay, so easy case, no recursive rules, right? So I'm not binding anything. I'm just adding the element that is put there by the base case. Okay, one run of recursive rules. Well, so we already went through this. If I run this rule, the only A is in this set, so it's recursive rule 1, A equal this, it's going to add this thing to it. And if I run recursive rule 2, well, both A and B have to be equal to this thing because there is nothing else in the set. And I'm adding this string to it. Okay, we've already done that. Now let's run recursive rules again. Well, let's try recursive rule number 1. Now I have choices. A could be this, this, or that. It makes no sense to use this because, again, I've done this here. So this will be added and nothing else. So let's just cut the chase and only consider new elements A here. So what would rule 1 add in this case? It will add open and then copy A, which is open, open, close, close, and then close again, right? So it's open, A, close. What about the same recursive rule? But I can use this guy as my A because he's also in the set. Well, what does it do? Open, A, close. Open, A, close. Okay, I'm getting this guy now. Rule second. Well, here I have many choices. A, B, C could be any of these in any order. The only uninteresting case is if A and B are both equal to this. All the other cases are productive. So let's take A, this, and B, open this one, right? What am I going to add? Open, close, close, open, sorry, this. What if B is this and A is the same? Well, this is my A and this is my B. By the way, I will generate this somewhere later again, right? So if I take B to A to be this string, I would just do that one to show something interesting happening. If A is this and B is this, then I'm actually adding the same string, right? So that was sort of a not good case, not a new case really. But if B is this, then I'm adding this string. And of course, if B is open, close, open, close, I'm going to have A, which is this, and then B, which is that, right? And a lot is being added already with two executions of the recursive rules. Moreover, some things suddenly there is basically two ways to get to this string. It can be interpreted as this could be A and this could be B, or this could be A and this could be B, right? That's okay, because again, adding twice the same thing is fine. It doesn't change anything, but there's nothing wrong with the definition that adds the same valid element again and again. I just want to point out something, that this code is very simple. It's a simple two rules. And yet, the number of objects it generates starts being quite rich. You might ask all sorts of questions about such recursive definitions. Let us start with the following. Well, how did I come up with these rules? So they seem to work. Am I sure that they generate all properly nested parenthesis strings? I would say that I'm rather sure that they will not generate something that is not properly nested. Okay, so you can try to define a notion of properly nested as you go through the string and basically you add a 1 when you see an open, and you subtract a 1 when you see a close, and a string is properly nested if always as you go through the string, you get positive balance or non-negative balance. You see, here you add your balance is 1, 2, 1, 0. Never negative. 1, 0, 1, 0, 1, 2, 1, 2, 1, 0. You add when you get an open and you subtract. And okay, let's say you define PNPS strings using that procedure. Okay, so you define all strings here as strings that if you go up, you go through them, you will maintain this positive balance or non-negative balance. Can you argue that these two rules will only generate strings with that property? We will use induction to do so. That induction has a name. It's called structural induction because it applies to structures that are recursively defined. But this is just a name. It's really one and the same thing as always. It's induction would be an argument that will be, you argue that some property is met by base cases, and then you argue that if it's met by these objects, then it also will be met by these ones exactly in the same way as we argued, as we used recursion before to argue that if something is held by if some predicate is met by say a function defined in this way, then it's also met by the next step in the recursion, that the output of the recursive call, so to speak, also satisfies this property. That's how recursion worked, and it will do the same for us here. But let's look at let's look at some other questions we can ask. So here is a recall of PNPS definition I gave was like this: base, this open close is in PNPS, and recursion, if AB are in PNPS, then both open A close is in PNPS, and AB is in PNPS. I had it as two rules, but you can just as well capture it as a single rule. That doesn't change anything, right? Okay, so that's one definition. How about this one, PNPS plus definition? The base is that an empty set is in PNPS. Recursive is the same as above. So if AB are in PNPS, then so is open this thing, sorry, I'm defining now PNPS plus. So if two elements are already members of PNPS plus, then so is this thing, and so is their concatenation. What is the relation between PNPS plus and PNPS? So if I use these recursive rules to build a set, do I get exactly the same set as here? Or would some other elements be created? Conversely, would something created in this way, what is the relation between them? Right, the relation is that PNPS plus equals PNPS union an empty string. So this really claims two things. First of all, it claims that every string built in this way can be built in this way. That's not a hard argument. It will be really an inductive argument, but it's so apparent that it actually earned that name. Let's argue by case. Is elements added by the base case created here? Yes, because this is an element added by the base case, and that guy is in PNPS star plus. Why? Because he's created by instantiating the recursive rule with an empty set, empty string. If A is an empty string, then this resolves to open, empty, close, which is open, close, which is this. So base case guy is in PNPS plus. He is generated by PNPS plus. He's not in the base case. He's created by this recursive rule instantiated with A equal lambda. So PNPS is Y. PNPS is a subset of PNPS plus because first thing we have to check, the base case thing is in PNPS plus because recursive rule creates it with A instantiated as lambda. Namely, this part of the recursive rule will create this as an element of PNPS plus. Okay, and So that's base case. And what about everything that is done in the recursive rule? So we are adding, if something is a member of PNPS, then that thing open, close, and, well, if two things, then open and copy, close, or concatenate are both in the set. Well, the recursive, so this is really recursive structural induction that we'll see basically next lecture, because we don't have enough time right now. But the argument will be recursive if n applications of this always created something that can be done using these, then so is n plus first application will also be here. So if you believe that n application of this recursive rule will create things which are only in PNPS plus, so therefore this is satisfied when you restrict the set to only n applications of the recursive rule, then let's see that n plus 1 applications will also get something here. Well, so that is the inductive argument. N plus 1 application instantiate A and B from the set, so these must be created using n applications. And by the inductive assumptions, they were already in here. So what you're adding is you're using A and B, which already was in PNPS plus, and what you're adding is this and that. Well, they would be in PNPS plus by this rule. That's the end of this argument. And also PNPS plus is in PNPS and you can reverse this argument and basically show that the only thing that is missing in here is an empty string. Okay, I'm maybe getting slightly ahead of myself with this, but I want to add, just end with some examples. They kind of leave it as a question mark for you. How about PNPS question mark, which will be defined like this? The base case is open close is a member of this PNPS question mark set. And the recursive rule says that if AB are members of PNPS question mark, then so is this. And instead of concatenating, I'm doing that. They seem natural enough. Would it, and perhaps you can see that, okay, yes, this will only generate properly nested parenthesis strings. If this is properly nested, then so is this. If both of these guys are properly nested, then I can definitely do that. But the question is, will it generate all of them? Here is a final variant, double question mark. And I'm going to change it like this. An empty string is in the double question mark PNPS. And the recursive is the same as above. So if it's in the double question mark, then so is A and open A close, open B close in PNPS question mark. Is it same as PNPS? Okay. Is this the same as PNPS? I leave these as a question marks, and you can post your answers on Piazza. Okay. We'll continue with this stuff next week. And of course, on Friday, there's a test from the previous 3 weeks. I will continue recording on the assumption that perhaps some questions you might ask will be referring to, will be useful for people who watch it offline. So yeah, the difference between these two, the difference is this, the base case. Okay, so you see, don't worry, if this is confusing. The problem with this stuff is that, okay, here is the meta point. Tiny difference makes a big difference, because these recursive definitions are really very powerful. And this tiny piece of code basically generates all properly nested parenthesis strings. They're very complex, really, in nature, right? Like, it's not so obvious how to parse, how to decide that a string is properly nested or not. I gave you a linear scan procedure, but I mean, it's not like so obvious. Like, I don't think like you will come up with the same linear scan procedure, in so short, right? So quickly. So, and because they're so concise, tiny change in the base case and a tiny change in the recursive rule have very powerful effects. They might miss some things down the line. They might completely generate different classes of objects. And what you should do is, now that you have seen me generate, and you'll see in the book, in exercises, how do the recursive definitions work? So run this procedure. Run this, make a similar type of table like we did, here. Number of applications and how you instantiate and what do you get. Don't try to shortcut. Do it by the book. Just use this stuff. See what it creates. And then see, something is missing. I cannot create something. Or maybe something is created that is wrong. So don't just like stare at this and declare, failure, like this stuff is confusing, I cannot do it. No, this is a simple code. It's not so hard to, instantiate this and see what is created, instantiate this and see what is created. Okay, you will not see this without this type of work. And now see what this kind of code does this. Only after you do it again and again and again, then you will basically be able maybe to do this in your head and get some intuition. You cannot ask you, and I do not expect you to have this type of intuition from the get-go. You have to do the work. I mean, it's not a very hard work, but you have to do the work. It's sort of very similar to the fact that recursive code is fragile. You change, remember this exercise from the homework where I say, is this an induction? And I modify tiny element in the base case. Instead of a 0, I do 1. Or I modify slightly something in the recursive case. I sort of offset a little bit. And then suddenly from a correct inductive argument, you get not an argument. Okay? It's the same here. These things are delicate. And okay. Do you want to say something? Because there's 99 comments on the chat. Oh yes, I will upload these notes for sure.
Professor, for 8.4 to 8.6 on Zybooks, could you show the solutions? Could you make them visible for the additional exercises?
Which exercises?
Zybooks 8.4 to 8.6, like for induction and strong induction.
Okay. None of them are open in your view because they're open in my view.
No, some are, but like some aren't because I'm just practicing like
Oh,
questions, so I want
yes.
to check my answers.
So look, the textbook writer asked me, do not open all of them. So
Okay.
I said, I will open half. Is half okay? She says, yes. So I actually open more than half. But I mean, if there is something you want me to open, I can open it, So just tell me which one.
Okay,
I mean,
I think
opening
I'll
one or two
later post
more,
that.
it's, huh?
Yeah, I think I'll come back to you later on that
Okay,
one.
just post it
Yeah.
on Piazza.
Okay, cool. Thank you.
Look. Any other
Professor?
questions? Yes.
Just a quick comment. I really like how you're doing the lecture now as opposed to just having the slides.
Okay.
I think, yeah, just some feedback. I like
Great.
this class a lot better.
Yeah, I'm glad. Yeah, I mean, this stuff is not very good for slides.
Mm-hmm. All right, thank you. Have a nice day.
Thank you so much. So I sent an email to everyone about the test, and there is like, basic thing was that it will. I'm not going to use any software to try to proctor it. And there were all sorts of other points, like how you should update, you should scan and upload, and this and that. The PDF will be actually emailed to you. Yes, and the extra time, I think 5 minutes after 1 is the threshold, because it's not. I think that it would be unfair if I gave more time, because then people who have a hard deadline and have to go on to something else, it will be unfair to them. So I said 1:05. Okay, great.